Professor Serfaty is a professor at Coulomb Institute of NYU, New York University. Professor Serfaty's research is in PDE, in mathematical physics, in probability, and in particular specializing in statistical mechanics and models of Coulomb gas. For her excellence in research, she has been awarded numerous prizes, and here's a select partial list of those numerous prizes. If I will give a full list, then you will hear me for the whole hour and not Professor Serfaty, which is what you paid for. So here's a partial list. EMS prize in 2004, Henri Poincaré prize in 2012, Maria Bourdieu prize 2013. She was a plenary speaker in ICM 2018 in Rio, and she was elected as a member of American Academy of Arts and Sciences. Professor Serfaty is an associate editor of numerous prestigious math journals. That includes Connections in Pure and Applied Mathematics, CIPAM, Forum Mathematicians Sigma, Journal of EMS, Journal d'Analyse, Asterisk, and she's a chief editor of Probability and Mathematical Physics. So with no further ado, we're going to listen to Professor Serfaty that is going to speak about systems of points with Coulomb interactions.
Okay, thank you very much. So today I would like to speak about various aspects of systems with Coulomb interactions, and let us start by describing what we mean. So I remind you the Coulomb kernel is an inverse power of the distance in dimensions larger than 3 at least. So it's 1 over x in dimension 3, and more generally 1 over x to the d minus 2. And if you're in 2D, you want to consider instead the minus log of the distance. So it's always singular at the origin, and it's always a repulsive kernel seen like this. So I want to consider n particles of same type located at x1, xn, and the energy Hn of this system will be the sum of the pair interaction energies with this Coulomb repulsion. There is a 1/2 here, and we add some external potential V, some additional confining potential. The role of V is to keep the particles together because due to their repulsion, otherwise the system would sort of spread to infinity. So you see here that the order, the size of these quantities is going to be of order n squared, and this one has an n in front just to keep it of size n squared, because you have n terms. And here you have nn minus 1 term, so it's all of order n squared. As n goes to infinity, of course, we're interested in this situation where n gets very large. So sometimes we can be interested in variants of this Coulomb interaction that I will consider. The logarithmic interaction in 1D, which is not Coulomb, but logarithmic, and Rees cases, which are general inverse powers of the distance. So that includes Coulomb, but that includes much more general powers. And of course, you could also consider the 1D Coulomb gas, which is then just minus mod x, but that I will not talk so much about, but it's been well studied. Okay, so we assume that this V is a sufficiently nice potential in the sense that it's sufficiently smooth, and it has to grow at infinity to actually have this confinement effect. Okay, so this is the setup. And now what type of questions can we be interested in? First natural question is just understand minimizers of this energy and how they behave as n goes to infinity. Second type of question is to be interested in evolutions. So here I wrote to you a few cases of interest. One is the gradient flow, the first one, where the velocity of each point is given by minus the gradient of the energy respective to that point's position, but you normalize by the number of particles. So it's written in a mean field regime, so that each particle feels the average force generated by the other particles. And here, this is Newton's law. Now you prescribe the acceleration of each point to be given by the average force. And the third set of problems is to be interested in statistical mechanics and look at states with temperature. So I will look at that towards the end of the talk. And first, let me start with the motivations and background and why we could be interested in these types of questions. A first motivation comes from approximation theory. It's Fekete points. So what are Fekete points? They are good interpolation points, or even best interpolation points. So let's say you want to approximate the integral of a function by a Riemann sum. If you're in a high dimensional setting or on a manifold or in space, you can ask yourself, where should I put these points for my sampling for computing my Riemann sum in such a way that the error is minimized, or the sort of worst case error relative to smooth functions is minimized. And it turns out that these are well defined. The optimal points are called Fekete points. You can characterize them. If you're in a manifold, it's easy to characterize them as maximizers of products of distances. But of course, if you look at product of distances, you are maximized. It's the same as minimizing minus log of the product of distances. And so that's the same as minimizing minus sum of log of distances. So you get back to a logarithmic interaction minimization problem on a manifold. And more generally, you can do this with weight. It has an interest for, it's actually related to orthogonal polynomials. And when you do it with weights and you take again the log, you see that it's the same as minimizing an energy of the form Hn, but again with a logarithmic interaction case. So there's a large literature on that from the point of view of approximation theory. And here is some pictures that you see there. These are Fekete points on the sphere. You see that they arrange themselves uniformly on the sphere, as they should, because you want them to well approximate the uniform measure. So there is this macro scale behavior, which is the uniform distribution of the sphere, but you can see also that there is an interesting micro scale behavior where you see pretty regular patterns of points that are of interest. So I will distinguish between this micro scale, the typical distance between 2 points, and the macro scale, which is the size of the whole object. And in approximation theory, people also are interested in this. Yes.
So the distance, is it in the embedding space distance, or it's?
Yes, it's the distance in the embedding space. Yeah. Yeah, the intrinsic distance. So you also consider, they also consider general inverse powers. So these Riesz energies like this. And what's interesting with that is it creates a whole parameter family of problems. You can see at one end, when S is close to 0, it's essentially equivalent to the logarithmic energy minimization. And on the other end, when S goes to infinity, you can show it converges to the best packing problem, which is the problem of packing the maximal number of hard spheres in a given volume, like here, right? So the problem which is solved in certain dimensions, particular dimension 2. So for all S, in fact, you see these types of pictures if you're in a sphere. It doesn't really seem to depend very much on S. And if you're in a more complicated manifold, you can see different behavior depending on S. Okay, second motivation comes from condensed matter physics and vortices. It's the topic. So I came to be interested in Coulomb systems for that reason, from this origin. By studying the problem of superconductors and superfluids that are, and Bose-Einstein condensates that are modeled by Ginzburg-Landau type functionals. So to give you a simplified, the simplest version of this, you can study these types of equations where psi is a complex valued unknown function, like a wave function. So this is called Ginzburg-Landau. This is the static version. This is called parabolic Ginzburg-Landau, the parabolic version. And the Schrödinger version is Gross-Pitaevsky. It's a well-known equation in in superfluidity. And as epsilon goes to 0, what happens is that the vortices, which are the zeros of the wave function psi, which come with a sort of winding current around them. So if you want a topological number, which is a degree, in this asymptotics where epsilon goes to 0, everything happens as if they were really purely points. And a lot of work was done on that to show that you can really reduce rigorously to a system of points with two-dimensional Coulomb interaction, which is the logarithmic interaction. So you start from a complicated PDE and you can derive this sort of discrete problem with large numbers of points with the 2D log case interaction. So that's a motivation, another motivation for this log situation, the log case. And of course, vortices in 2D classical fluids also have a similar phenomena where, you know, the point vortex system is also a system with points with logarithmic interaction, etc. So in superconductivity, what's good is you have experiments and you see how the vortices present themselves. You can see on those pictures, they form these Abrikosov lattices. So Abrikosov is the name of the physicist who predicted the emergence of such periodic configurations from the Ginzburg-Landau model. And you see they form really quite perfect triangular lattices here in superconductors. You can see them as well in superfluids or in rotating Bose-Einstein condensates. Okay, third motivation, that's for the situation where we add temperature, where we would be interested in looking at statistical mechanics. It's from statistical and quantum mechanics. So again, the logarithmic interaction cases, whether it's 1D or 2D, are motivated by things from theoretical and statistical physics, in particular random matrix theory. When you look at a random matrix and you throw the entries at random, you make them Gaussian IID, that's the simplest thing. With symmetry or without symmetry, you can write the law of the eigenvalues, and the law of the eigenvalues is always that of a log gas. So the eigenvalues always repel themselves logarithmically, and there is a large, very large literature on that, on random matrix theory. Other models from quantum mechanics, such as a fractional quantum Hall effect, also give you Coulomb gas problems. So there is a very comprehensive book by Forrester that describes all that. Then there is just a classical Coulomb gas as a toy model for matter, in particular for certain, for stars, for astrophysics. It can be a reasonably good model, even though it's classical and not quantum. It's a difficult model because it's always a long range interaction, the Coulomb interactions. It doesn't decay very fast. And the particles are not on a lattice. They interact with all the other particles. They are free to be anywhere in space. So it's a delicate model of statistical mechanics, and certainly one of the fundamental ones. And finally, again, the dimension 2 logarithmic case has other connections with theoretical physics. When you consider particles that can have opposite signs, so possible pluses and minuses, then that's also sometimes called a Coulomb gas, or a two-component Coulomb gas, or two-component plasma. And that's related to things like the XY model and the Kersterlitz-Dowless phase transition. Okay, so I finish with my set of motivations, and I'm sure I've omitted some, but I want to go back to the questions we want to try to understand. First, the macroscopic distribution of the points as n goes to infinity that I described a little bit at the beginning, and also the microscopic behavior, obviously. And that goes together with questions of asymptotic expansions of the minimal energy. For instance, if you look at Fekete points on a sphere, there is a conjecture which says that the minimal energy should expand like this in powers of n. So you have a n squared term as a leading order with the coefficient a. That coefficient is actually not difficult to find. I will give it to you in a few minutes. Then you have an n log n term that's also not hard to guess from purely scaling considerations. Then you have an n term, And this coefficient B, now it's what we can access now. We have like results that allow us to find B. And then there's supposed to be log n terms and order 1 terms and then lower order terms, but these we have no idea how to describe them.
Excuse me.
Yes.
Excuse me. Can you say something? What is the heuristic behind the scaling with n?
The fact that there is such an expansion?
Yes.
Or the fact that
Is
there
there
is n log n?
a physical motivation or?
Well, you.
No, in general, this I guess n squared comes from the fact
N
that
squared comes from the order of
the
number of particles, yes. N log n, you will see later, it just comes from the fact that we have the logarithmic interaction, and the typical distance between particles is n to the -1 over dimension. And then after that, it's not so clear. Why is that? But there are some cases in which we can prove this. So if you look at the case with temperature, with beta equals 2.
For example, okay. So why, for example, these corrections are all analytic in n, not, I don't have n to 1/2.
Yes, you will see that there is going to be some n to the 1/2. There is some n to the 1/2 in some cases, in fact. So there are some physics papers that derive these things from explicit computations of integrals. And the n to the 1/2 shows up when you have a boundary. So here, because you're on a sphere, there are no boundary terms, and you will not see the n to the 1/2. But if you are on the plane and you had a region with points, then you would have an n to the 1/2 term. So this is you have some physics computations that derive these things that are not easy. It's actually the whole point of the work is to try to derive these things.
Okay, thank you.
And why these exponents come up, I don't think I can give you a very good heuristic, except that there are some terms that are proportional to surface terms. So it's like volume terms, surface terms, and that's how you can guess these powers. But the log n here, for example, I have no idea why it's there. It's not, I don't have a good explanation. Okay, so let's move to the next chapter, which is to start by describing this macroscopic behavior. So that's also called the mean field limit. So what we do is we look at these empirical measures, right? So sum of Dirac divided by n, that's a probability measure, and we try to derive the limit as n goes to infinity in the various settings that I described. So time independent, time dependent, with temperature. So first for minimizers, it's quite easy. So I remind you what the energy is like. It turns out that there is a limit for minimizers, which is called the equilibrium measure. So it's denoted here mu v. And the minimal energy will scale like n squared times E of mu v. So this is a particular constant that you can characterize as the minimum of this functional. Okay, so what you do is you write a sort of continuum version of the interaction energy, but now it's integrated with respect to probability densities. And you don't have to worry about the self-interactions anymore. So here you remove the diagonal, here you don't have to do that. And this thing now is strictly convex, it has a unique minimizer. It's like the basics of potential theory to find that there exists such a thing if V grows sufficiently fast, and that's the equilibrium measure, the Frostman equilibrium measure. Now the minimal energy is of order n squared, as we had sort of predicted before. And minimizers converge to this. Okay, so this actually would make sense for any interaction as long as this thing is integrable near the diagonal. So as long as W is integrable near 0, which, if you're interested in the Rees cases, forces the power to be strictly less than D. So that's called the potential regime. If S is strictly less than D, you can understand things like this.
Sorry, could I ask if the external potential has a double well, then the minimum is not unique, I would guess, right?
No, that doesn't change anything. The potential has double well, but the energy is still strictly convex because that part is linear in mu, this part is convex in mu. So the potential, if your potential has double well, just means that your equilibrium measure may have two components, may have two connected components to its support. Right, you have a probability density.
Okay.
It's going to distribute itself between your two wells, for instance. It will still be unique. The uniqueness doesn't change. So this thing is true under very mild assumptions on V. You don't need anything special, no convexity or anything. Okay, so there are some cases in which we can identify this equilibrium measure quite well. One is when V is quadratic. Then in all the Coulomb cases, mu V is going to be an indicator function of a ball. So normalized now. So it's going to be a uniform measure in a disk by symmetry, just simply. That corresponds to the circle law in probability in random matrix theory, in fact. And another case that's well known and famous is the quadratic confinement for the logarithmic case in 1D, which is not Coulomb. Then the equilibrium measure is a measure with density whose graph follows a semicircle. So this is the density of the measure from 0 to 4 here. That's called the semicircle law. And this is the histogram of eigenvalues of symmetric random matrix ensembles. You see they follow this semicircle law. So we would always assume that mu V is a nice measure in the sense that it has a density, the density is regular on its support, it has compact support. And I identify in my notation the measure and the density of the measure. They are denoted the same way. Okay. So now I said we can also look at this question for the time-dependent case, so for the dynamics. So now I need to introduce, given the distribution mu, like a probability density, like before, the potential, the Coulomb potential or the Rees potential, depending on what I'm looking at, is denoted h mu, just the convolution of W and mu. Right? So it's this. So that's the potential generated by the distribution of charge mu. And now the total mean field potential is going to be this thing h mu plus V, the external potential, and the mean field force is going to be plus or minus, actually minus the gradient of this thing. And now if you wanted to look at gradient flows, so I go back to the question that I had posed here. Right, if we're interested in this, in the gradient flows, we can try to derive formally the evolution of the density that is going to be solving a PDE, right? So we enter a PDE world now. If we want to understand how the density of points evolves. And you can see formally, this should be the equation. The time derivative of mu is the divergence of this force, you see, multiplied by mu. Because you remember that each point feels the average potential generated by the other points. And of course, it comes with an initial data. And this says that the density is transported, you know, with velocity field equals to this force. And I remind you, this identity that if you time differentiate a Dirac mass at a moving point, it's minus the divergence of the velocity times the Dirac. And so here, if you plug in for the velocity, what you get from the ODE system, this is what you should get. So this is a formal back of the envelope computation. The difficulty here is that you have non-linearity. You see, you have h mu here, you have mu. So this is non-linear. You have things like that, h mu times mu. Plus W is singular. So it's not going to be easy to just take the limit as n goes to infinity in these equations and derive them. So in fact, it's been an open question for quite a while. So the 2D log case was known for a long time, actually from the fluids literature with the work of Chauchet, the point vortex system. Then there were results that worked up to the Coulomb singularity, because d minus 2 is the Coulomb case, or in dimension 1, because dimension 1 is special because the interaction is convex in dimension 1, which is not in higher dimension. And then there was this work by my student Durinx that works for low dimension. And I'm going to show you now an extension of this work, which is that now you can do all these Coulomb cases. So that's d minus 2 or the log if you want into d. And also you can do Riesz cases as long as it's super Coulombic. So between d minus 2 and d being a threshold, I explained to you a potential threshold. That's natural. Above d, it's a different story. And if you have the system of gradient flow, ODE, the system of ODEs, which is the gradient flow with some initial data. If your initial data is sufficiently nice, you have regular limit and you have a well-preparedness of the initial data, then up to the maximal time of existence of the solution to the PDE, you have convergence of the empirical measure to the solution to this equation I announced before in the box. Right? So the limiting equation with the proper initial data. So that gives you the mean field convergence. The capital T, yeah.
So you said it's singular, this kernel, but so integral is still convergent. So are you saying there is something else, extra terms in the actual limit when n goes to infinity, or just the way you interpret this equation?
There is no extra term. What do you mean? You can you get this
said
thing.
that if you naively take this as a limit and to infinity, then it's not enough, or it's hard to prove that it's true.
It's enough. It's the right limit if you naively take the limit. It's the right limit, but just if you want to make a proof.
All right. Okay.
You run into trouble making a proof that's rigorous, but the limit is correct. And the maximal time of existence now is a PDE question about that limiting PDE. And there are some cases, all the Coulomb cases, we know that the existence time is infinite. So there is no problem. There is no limitation in time. In fact, all cases for S less than d minus 1, you have infinite time of existence. Above d minus 1, it's open. Okay, so this also corresponds to something that's called propagation of chaos. If you can show things that the empirical measures converge like this, you have what is called propagation of chaos. Okay, there were some improvements to this result after that. So the case with noise was handled by Bresch, Japin, and Wang. There is a nice improvement by Rosenzweig to have less strong assumptions on the initial data and things like that. I also proved similar mean field limits for the Ginzburg-Landau dynamics. So starting from these PDEs I showed you at the beginning, the parabolic Ginzburg-Landau, the Schrödinger flow, you can derive rigorously in a similar philosophy some fluid-like equations. So this is a series of works by other authors, but then myself. Okay, now if you're interested in Newton's law, you remember the acceleration equals to the force. That's actually the more physical problem. Then the formal limit has to be phrased as a kinetic equation. It's actually a Vlasov-Poisson equation. So it's now an equation on the density of particles that are at position x at time t, but have velocity v. And deriving this rigorously in the Coulomb case is a major open problem. So with Durinx, we have a partial result, which is only when it's called the monokinetic case, or at each position there is a unique velocity. But the general case is quite open. So there were proofs for the sub-Coulomb case, but not for the Coulomb case. So that's to advertise a hard problem in the field. Okay, now let's pause for a second and let's go back to what we've done. We've seen mean field results for either minimizers or time, dynamics problems, but none of them was really completely specific to Coulomb. They work for all smooth interactions, no problem. Also Reese interactions for S strictly less than D. So far we haven't really used the Coulomb nature of the interaction very much. And what is specific to Coulomb is that the Coulomb kernel is the fundamental solution for the Laplacian, as you know. And the Laplacian is the best, operator you can think of. It leads to elliptic equations, regularity properties, etc. So now we're going to start using really more critically the Coulomb nature of the interaction. And let me show you how. So it's all about these potentials, Coulomb potentials, h mu equals W convolved with mu. And now I assume that W is the Coulomb kernel. I'm not going to discuss so much the other cases. So it's really Coulomb. Now for Coulomb, I have minus Laplacian W equals the Dirac mass, right, up to a multiplicative constant, depending on dimension. So the potential h mu solves this elliptic equation, a Poisson equation, if you want, minus Laplacian h mu equals some constant times mu. And what's very important is that this equation is local. It's a local operator, the Laplacian. If you were to take a general W, you could write things as a sort of Fourier integral operator, but it wouldn't be local. So that's really the specificity of Coulomb. And so now I can rewrite things like this. If I have two probability densities, for instance, or two measures of same mass, mu and nu, I can define a norm, a Coulomb norm squared to be this. Wx minus y, d mu minus nu of x, d mu minus nu of y, which can be rewritten as a convolution, W convolved with mu minus nu, again integrated against mu minus nu. But now this I can rewrite as the potential, h mu minus nu by this definition. And mu minus nu, I can view it as the Laplacian of the potential up to this constant. And now you see that with this form, now I'm tempted to use Green's formula and integrate by parts, which I can do because there is actually things decay at infinity. And the way I've chosen them of same mass, there is no boundary term at infinity. And so if I integrate by parts, I rewrite this as the square of the gradient of the potential generated by mu minus nu. So this whole double integral, which contains interactions between mu and nu, can be rewritten as a single integral in terms of the potential, in terms of the Coulomb potential, or if you want, the electric potential generated by mu minus nu. And this is a Dirichlet energy, it's the simplest possible energy you can think of. And that now becomes local. So this interaction that was non-local is becoming something local in terms of the electric field. And we actually work with that to make, to localize things and to analyze these energies. Okay, so this Coulomb distance is what is used to show the time dependent, the results on the dynamics that I presented just before, when I showed you the empirical measures converge the solutions to this PDE. The way to do it is to differentiate in time the Coulomb distance to the expected limit and to show that it satisfies a Grandval relation. And then you use Grandval's lemma to conclude. So if you're initially close, you remain close. And the way to measure this closeness is to use this Coulomb distance. That's the way around this whole question of taking limits in nonlinear singular terms. Okay, if you were interested in these Reese kernels with S between D minus 2 and D, that also we could do because there is an extension procedure that allows you to reduce the corresponding operator to a local operator in extended space. But let's focus on Coulomb for the explanations. Okay, so now we can start thinking about going to the next order and expansion of the energy. And going to next order is also going to give us information on the microscopic behavior of the configuration. So in fact, the leading order encodes the macroscopic distribution and the next order encodes the microscopic distribution. So that's what I want to show you. Okay, so the main approach is that we want to expand things now. We're going to expand around this equilibrium measure, which we know to be our mean field limit. So let's think of minimizers. Let's go back to the question of minimizers for now. And now we're going to introduce this potential, electric potential, Hn, generated by the distribution. I'm going to make the difference between the sum of the Diracs and the expected limit, which is n times mu v. So you see here, I don't normalize by n, but this is also a distribution of charges, which is neutral. The mass of all this is 0. So you have n positive discrete charges, and you have a negative charge of mass n, but which is continuous. You see, it's well distributed. Mu phi is nice. And so this system is electrically neutral. Its potential is Hn. And we can rewrite the next order energy by the computation I showed you before as the Dirichlet energy of Hn. So it becomes integral of grad Hn squared. And because of the locality of this quantity in terms of Hn, we can devise something that we call a screening procedure that serves to basically be able to cut and paste configurations and compute the energy additively over cubes. So suddenly these questions of looking at interactions of far things becomes reduced to something much simpler, which is an almost additivity of the energy. And now to give you the first result that we obtained that way, there's this picture. So we have the support of the equilibrium measure, right? So this is where we know that points typically will be. And now we're going to zoom because we want to look at the microscopic this situation. So we want to zoom at this scale, mu v of x times n to the 1 over d, because that's exactly the typical distance between points, or the inverse of the typical distance between points. So when you zoom at that scale, you expect that the density of points should be now 1 after the blow up. You know, after this blow up procedure, there's about 1 point per unit volume. So every time you zoom, you see a configuration. So here near this green dot, I see one configuration. Here this red dot, I see this one. Here this blue dot, I see this one. And we're going to define an interaction energy for these infinite configurations of zoomed configurations. When n goes to infinity, these things, they end up filling the whole space, right? So they converge to infinite configurations. And we define a total Coulomb interaction energy of these configurations of the Diracs at these points, minus 1, which is meant to be the neutralizing background that we had here. So this becomes minus 1 if you zoom properly, and this becomes the sum of Diracs. So in physics, that's called a gelium, a system with positive charges and a uniform negative background. And the total energy now of the whole configuration here is going to be the average W bar of this energy W when I sum over all the blow-up centers, because I have to compute the energy here, plus the energy here, plus the energy. So in fact, I have to average over the blow-up center. And so let's say, here, if here I zoom and I see a triangular lattice, then I have the energy of the triangular lattice. If here I zoom and I see a square lattice, I have to compute the energy of the square lattice. And if it's half the time this one, half the time the other, then my energy will be half of the energy of the triangular plus half of the energy of the square, for instance. Okay, so we were able to show that the energy, actually it's in Coulomb case, but also all these log or Rees cases that I mentioned before. So in series of works with various collaborators, we showed that you can expand the energy to next order indeed. So there is the leading order that we had seen before, n squared E of mu v, that was the term from before. Then there is an n log n term, which is in light blue because it only arises when you have the logarithmic interaction. It's due to during the blow up, the scaling of the log. And then the next order term really is the power n to the 1 plus s over d. So with the note that if you're in the log case, so for example, the 2D logarithmic interaction, you should take s to be 0 there in this formula. So then it's just n. So in any case, it's always a lower order term. It's a lower order power. And it's this W bar, which is to be defined on these infinite blown up configurations, blah, plus little o of this. Okay, so now that already gives you something about minimizers of the energy. If you want to minimize the left-hand side, you should minimize the right-hand side. And because this is all constant, you have to minimize this W bar. So we have derived a limiting minimization problem. And minimizers are such that after blow up around almost every point, you see a minimizer of this W, which I haven't defined completely for you, but it's built by, it's basically defined as a limit of these things here. Okay, so that sort of can be adapted to the 2D sphere and give the first coefficient in this conjecture I had given you, a Fekete point on the spheres. This is also adapted to the full Ginzburg-Landau model of superconductivity. In fact, we started by proving it for Ginzburg-Landau. And you have much stronger results for minimizers than what I said. So it's not only almost every point, it's really a uniform distribution of points and of energy at any scale, which I will not describe here. But now we get to this question of minimizing this W. Yes.
Sorry, can I ask, in the previous slide, I must have missed, what is the order of magnitude that you expect from W bar? So why is n to the power 1 plus s over d smaller than n squared?
Because W bar is of order 1. I expect that it's something that doesn't depend on n anymore. It's the energy of an infinite configuration. There is no n in it anymore. So this should be of order 1.
I see. So this is really bigger than, okay, n log n, okay, my bad.
N log n is bigger than n, right? It's a smaller order term.
I see, okay.
Always, yeah.
But n to the power, I don't understand something. N to the power 1 plus s over d.
Yes.
Isn't that bigger than n log n?
Okay, so n log n is only there when s is 0, when you're in the log case.
Ah, I see.
And log n, that's why I put it in light blue, because you
that
should.
Explains that.
Okay, so if it's not a logarithmic case, there is no n log n term. You only have the powers.
So n log n is instead of the n squared in the logarithm case. Okay, I got it.
So if you're in the log case, you have n squared, n log n, and n. If you're in the Rees cases, you just have n squared and n 1 plus s over d.
Okay, very good.
I just tried to put everything in one formula, but maybe it's confusing. And 1 plus s over d is always less than 2.
Yes, that I agree. Yes.
That you agree, right? So that's why it's always in this order. And W bar is computed for limits. It's an energy on limits, so it has no n in it anymore. So either it's infinite or it's finite. That's all. So the things that have infinite W bar, they can exist, but they're just not good for minimizing the energy.
When s becomes equal d, then your integral stops converging, right? In this limiting.
Yeah, when s becomes d, it's another problem, because now we have this, it's not potential, you don't have an equilibrium measure. So at s equals d, everything has to be studied differently. It's called the hypersingular case. Actually, we did things for s bigger than d in works with Thomas Leblay, Hardin, and Saf. We studied that case as well. In a way, it's easier when s is bigger than d. And the reason why s bigger than d is easier is because you have a much faster decay of the interaction. And so when you have fast decay of the interaction, the additivity of energy becomes easy. It's easy to separate, to make boxes independent, essentially. So we also studied it, but I didn't mention it here. This case is actually harder from a certain point of view. Okay, so I want to talk to you for a few minutes about this question on minimizing W, which is pretty interesting, because we reduce ourselves to this new minimization problem on infinite configurations of points, which are normalized to have density 1. Okay, so if you're in 1D points, you normalize to be density 1. You can prove with convexity arguments, not difficult, that the minimum is achieved when you put the points exactly on the lattice Z. Remember, density is normalized, so you should put them regularly. This thing prefers points to be put regularly, and remember, it counts a total Coulomb interaction of the points together and the points with the background, with the negative uniform background. Now, what about higher dimensions? There are So there is a conjecture by Cohn and Kumar that said that there are some special lattices in dimensions 2, 8, and 24. So in dimension 2, the triangular lattice that we've seen in the experimental pictures. In dimension 8, the E8 lattice. Dimension 24, certain Leach lattice. And these lattices should be universally minimizing, which means that they should be minimizers for a very broad class of interaction energies, all interaction energies that are completely monotone. And that you can show implies that our W is minimized by these same lattices. So we prove that it also covers this case. That also includes sphere packing, by the way.
Am I mistaken to think that this is this conjecture was proved by Vyazovska or not?
Yeah, so wait until my next slide, because I explained that, so this is a crystallization question that's typically difficult, but it happens that in dimensions 2, 8, and 24, you can say something. And yes, Vyazovska solved the sphere packing problem in dimension 8, and that opened the door to solving this full conjecture, which is not just for sphere packing, but for general interactions, in dimensions 8 and 24. So that was solved, just what I said is solved. So the question of minimizing W in dimensions 8 and 24 is solved, but dimension 2 remains open for now, which is quite fascinating. Especially your dimension 2, you really believe in it because we saw it in superconductors. We extracted the energy W from the energy of superconductors, etc. In high enough dimensions, minimizers are not expected to be lattices. So there should be other configurations that are better than lattices. And in all the intermediate dimensions between like 1 and 10, it depends on the interaction. So some lattices are expected to be better than others. And so for this particular Riesz or Coulomb interaction, you know, some lattices should be the best, but nothing is really proved. So it's all quite difficult. And so we're left with this conjecture in dimension 2. The triangular lattice should be the global minimizer, but we don't have a proof. As I said, it's supported by the observations. And there are some partial results, conjectures about the, in dimension 2, there's a partial result that is among lattices. If you take Bravais lattices, what is the best lattice? Well, it is the triangular lattice. That is proof. That's related to a number theory result from the 50s about the minimization of the Epstein zeta function. In dimension 3, it's expected to be BCC, but that's not even proved. It's not even proved that it's the best among lattices. Okay, but at least dimension 2, we know that the triangular lattice is the best among lattices. So W distinguishes between a square lattice, for instance, and a triangular lattice. Okay, so we have derived this minimization problem, which reduces to a very difficult question in number theory in a way, whose answer in dimension 2 is expected to be triangular lattice. Answer in dimensions 8 and 24 is known, and 1 also. And the other dimensions is also completely open.
I could ask, to which extent those conjectures can be tested numerically?
It's actually hard because the problem is when you try to compute minimizers, these energies have a lot of local minima. As n goes to infinity, they have more and more. So you are never sure that you have not converged to a local minimum instead of the minimum. Mm-hmm. So of course, numerically, it seems to a perfect agreement that you see the triangular lattice. But it could very well be that this could be it could be stuck in a point of local minimum because these things have a lot of complexity. You know, the energy landscape is very rough. Okay, so I will use the end of the talk to discuss a little bit the situation with temperature when you want to do statistical mechanics. You know, so you form the Gibbs measure now, and you said that configurations are random and they are drawn with probability proportional to the exponential minus beta times the energy, where beta is an inverse temperature, and Z is the normalization that makes this a probability. So it's called the partition function in physics. Okay, so it's configurations with low energy are favored, but it's not as simple because now you have a question of volume. You know, what is the volume of these low energy configurations? How much do they weigh in the integrals? So there is also a conjecture, if you want, about the expansion of the free energy. So now the free energy replaces the energy in this context. You should take the log of the partition function and divide by beta, for instance, -1 over beta. So that's the free energy. And again, physics papers tell you that, say, in the 2D log case, you have an expansion like this. So just like before, now the coefficients, they may depend on beta. And they are actually quite interesting to physicists. In particular, if you play that game on a manifold, on a Riemann surface, then these coefficients have a geometric interpretation that are related to also field theories and things like that. So again, the A coefficient will be easy. The B beta coefficient we can get, and beyond, it's very hard, except if you're in dimension 1. Okay, so what is the mean field behavior? We start again with the same plan, right? The mean field behavior is still that you look like the equilibrium measure. The temperature doesn't really kick in at this stage. So except with exponentially small probability, there is something that's called a large deviations principle that expresses this, but it's not important to state it, I think. But now when you look at the pictures, you can see a simulation of a 2D log gas with the quadratic confinement. So everything is radial. The equilibrium measure is the uniform density in a disk. You see the points distribute themselves uniformly in the disk, but on the left-hand side, I have beta equals 400, and the right-hand side, beta equals 5. So beta being an inverse temperature, it means the thing on the left is much colder than the thing on the right. And you see the effect, not on the macroscopic distribution, but at the micro scale, you see something much more ordered on the left-hand side and something less ordered on the right-hand side at the micro scale. And this is what we would like to describe, right? So let me show it to you again in a different. So we're going to reduce temperature progressively, and you see things getting more ordered until, maybe until you believe you are getting somewhere near this triangular lattice. No? Okay, so this is going to be expressed in terms of point processes now, which are random configurations of points. Let me show you for reference. On the left-hand side, the Poisson point process. On the right-hand side, so Poisson is, you know, when you throw your points independently, uniformly, they don't feel each other, they're independent. On the right-hand side is the Gini point process, which is the only non-1D point process that we know in this business, that we know explicitly. So it's what happens when you take beta equals 2, quadratic confinement, and log in 2D. Turns out the beta equals 2 case has some particular properties. It's determinantal, so it's integrable. You have things that can be computed explicitly. And you see the repulsion between particles, they seem to be more, better distributed than in the Poisson point process. And so the result we were able to show with Thomas Leblay is that, I'm stating it in a slightly informal way. So it works for the log interaction, the Riesz interactions, again, in this interval between d-2 and d, so super Coulombic. We have these limiting point processes that we obtained by zooming, just like in my picture before. And Px is going to be the point process seen when we zoomed around x. So the Gibbs measure concentrates on configurations whose limiting point processes minimize this functional. So that's the important thing, this function. So it's phrased in the large deviations principle language, but maybe you don't need to know that. There is a function of the point process to be minimized, and this function is the average of W, the same function as before. But now we add a relative entropy term, more specific. It's called a specific relative entropy, It's the relative entropy of the point process with respect to the Poisson point process, and there is 1 over beta in front. So we just have to minimize that to understand a bit what configurations do. So if beta is very large, you can delete this part and you just find that you should minimize W. And this is what we saw before. If we believe that W prefers very rigid configurations, that actually proves a certain form of crystallization, at least in 1D or in dimensions 8 and 24. When beta is very small, on the other hand, that's very large temperature, then this dominates. You can neglect W and you're just trying to minimize the relative entropy. Relative entropy is a bit like a distance, so it's minimal when this thing is equal to that thing. So you actually converge to the Poisson point process. You can prove this one. And in between, well, it depends on the temperature, but you have something with the two weighing in a similar way. And that's what we saw for the Gini point process, which was beta equals 2. So there's a competition between rigidity, regularity of crystals, and a certain disorder of the Poisson point process. Whether there is a phase transition for crystallization defined in a different way is a also very important open problem in the business, but maybe I wouldn't have time to talk about that. This is something to say that we did study the case S bigger than D, and S less than D minus 2, which is more regular, is actually open as far as I know. Okay, so as a corollary of this result, we obtained the next order expansion of the free energy. As I had announced to you, we can also only get the next order term after the n log n, but not beyond. This was known in dimension 1, but not in higher dimension. And we also able to show the existence of a limiting point process after a subsequence. So that I don't have time to discuss this, but we're able to show this rigidity not only at the macro level, but down to micro scales. And the last result I want to mention before finishing is that we can prove some sort of central limit theorem on the fluctuations of the Coulomb gas in 2D, and now also in 3D I can do something, which is that when you look at the sum of the Diracs and you subtract the equilibrium measure minus n times mu v, if you test that against a smooth test function, you do what is called looking at smooth linear statistics. This thing actually converges to a Gaussian distribution with a mean which is explicitly given here in terms of f, and a variance which is also explicitly given. And that tells you something very strong about the rigidity of the distribution of points, because you see here, you don't have to normalize. You don't divide by n. You don't divide by square root n like you would in a standard CLT for IID random variables. This thing is actually of order 1 on its own. So that's quite strong. And it's also valid for functions f, test functions that could be supported at microscales if you want. So first it was proof from any mesoscale, but now it's extended to microscales in this work. And again, previous results, they were either in 1 dimension, the analog of this, or in 2 dimensions, this beta equals 2 determinantal case. So there is a limiting object underlying this, which is called the Gaussian free field, and you can see the picture here. A reformulation of this result is that the electric potential, which is defined like this as this inverse Laplacian, is shown to converge to this Gaussian free field, this sort of object that now arises quite commonly in probability as a universal object, a bit like Brownian motion is in 1D. And I will conclude. So I hope I convince you that the analysis of Coulomb systems is at interesting crossroads between different branches of mathematics, because it involves some, we've seen some analysis, some PDE, some probability, a bit of number theory, some geometry. Large Coulomb systems exhibit collective macroscopic behavior that was understood by mean field theory. The microscopic behavior you can understand by going to next order, and then you've are led to these crystallization conjectures and questions. A key tool is to phrase the energy in terms of the Coulomb potential generated by the configurations. And then I told you this makes things become local and additive. And the approach also works with temperature. It shows rigidity and Gaussian nature of the fluctuations, and this variational characterization of the limiting point processes with this minimization of competition between order and disorder, minimization of energy plus 1 over beta times entropy. And of course, many questions remain, one of them being how many of these features are really specific to Coulomb interactions or these interactions. We've used the Coulomb nature of it in a crucial way, but is it really a limitation of the Coulomb systems? And I thank you for your attention.
Okay, let's thank a speaker and unmute ourselves for a wonderful and very stimulating lecture. So let's thank. Are there any questions?
Yeah, I have a question.
Please do.
So I wonder, so I would expect naively the main correction would come actually from the boundary of the distribution near the, so did you assume that it's kind of covers the whole, support covers the whole space in what you've told?
Yeah, so the next order correction indeed seems to be a boundary term. It's n to the 1/2. But yeah, we don't access that for now. So we don't need to make any assumption because we only discuss the order n term. But if you want to get to the next order n to the 1/2, you have to work more, and I don't know. And maybe, yes, if you work in a torus or something like that, you could avoid seeing that term. But again, this is out of reach from our current techniques.
Just I know in matrix models and also in integrability, these terms I think were systematically computed. It's not exactly Coulomb, but in some cases I think you can take Coulomb limit. Yeah,
and also in dimension 1 you have full expansion to any order of powers of 1 over n in analytic cases. So, but if you're dimension 2 and you have these boundary effects, it's very hard. Yeah. I don't know how to do it.
Okay, may I ask questions, Sylvia?
How are you?
Hi, Sylvia. Nice talk. So for the mean in one of your formulas, in last formulas, for the mean of the difference between, convergence to the Gaussian field, it seems that beta equal 4 is just special point that mean vanishes or something.
Yes.
Yes, this formula. Is there some nice explanation for this, or it's just coincidence that beta equal 4?
Yeah. I think I used to know and I forgot, but
so it's not a coincidence. There is some feature behind it.
It's something that was already observed by, I think, the original papers of Dyson. He already had this beta equals 4 cancellation. If you look at his papers, to me, it's a bit of a coincidence of two things. There is a cancellation between two entropy terms. One comes from the actual entropy of the problem, and one comes from the energy being logarithmic. When you scale it, it also looks like an entropy term. So if you want mu log mu comes twice. It comes one as a real entropy and one as a logarithmic energy, and one comes with a beta and one comes with a 4 somehow. And because, you know, and that's the cancellation that happens, and that was already observed by Dyson.
Yes, whether this implies some other special feature, I don't know, integrability or whatever for beta equal 4, something like for beta equal 2. You mentioned that it's special. But...
I don't have the answer to that. I think you should know better than I do.
No,
but
I remember I've seen it somewhere, but it just was striking point that its mean vanishes.
it is, but it is, yeah, it is an interesting point. From my point of view, my explanation is just that you have this cancellation between two terms that are coincidentally the same and that cancel just when beta equals 4, but there might be a deeper explanation or a better way of thinking of it that I don't have. But yeah.
Any other questions by anybody? Okay, so in that case, first of all, I will stop the recording, and I suggest we proceed